Before time began, there was nothing we would recognize. No stars, no galaxies, not even space or time itself. Physics as we know it breaks down at this frontier, and yet, out of this strange beginning, our universe was born. This is the story of that first great moment, the Big Bang, and how it set into motion everything that would follow. Around 13.8 billion years ago, the universe leapt into existence. It began smaller than an atom, hotter than the core of any star, denser than anything we can imagine. Then, in a fraction of a second, it expanded at unimaginable speed. This process, called cosmic inflation, stretched space itself, smoothing out irregularities and laying the framework for the cosmos. In that instant, the fundamental forces of nature began to separate. Gravity pulled at mass, the strong nuclear force bound particles together, electromagnetism shaped energy, and the weak force guided the transformations that would soon create matter. In the opening seconds, particles flickered into being. Quarks, the smallest building blocks, combined to form protons and neutrons. The universe was a storm of radiation and matter, colliding, breaking apart, and forming anew. Temperatures were trillions of degrees, so hot that no atom could yet exist. The cosmos was a cauldron, but it was cooling. Every fraction of a second stretched the universe larger, and as it expanded, its heat dropped. The stage was being set for stability. By 3 minutes, the universe had cooled enough for protons and neutrons to stick together. In this short window, the first atomic nuclei formed. Most hydrogen, some helium, and tiny traces of lithium, nothing more. This is called Big Bang nucleosynthesis, and it provided the raw fuel for stars to come. These light elements are the foundations of everything: the stars, the planets, the oceans, even the air we breathe. All would trace their roots back to this brief creation of matter in the earliest moments of time. For hundreds of thousands of years, the cosmos remained dark. Atoms could not yet form. Photons, particles of light, scattered endlessly off free electrons trapped in a fog. But around 380,000 years after the Big Bang, the universe cooled enough for electrons to settle into orbits around nuclei. Hydrogen and helium atoms finally formed. For the first time, light could travel freely. This light still exists. Today, we see it as the cosmic microwave background, a faint glow in every direction, the universe's baby picture. With satellites and telescopes, scientists can read this fossil radiation, mapping tiny fluctuations that would one day become galaxies and stars. The universe's dark age stretched on for hundreds of millions of years. Hydrogen and helium drifted in vast clouds. Then, around 200 million years after the Big Bang, gravity pulled these clouds together. The first stars ignited. They were giants, far larger than our sun, blazing hot and short-lived. In their fiery cores, hydrogen fused into heavier elements. When they died as supernovae, they scattered these new elements, carbon, oxygen, iron, across the cosmos. Out of stellar death came the seeds of life. From clusters of stars came the first galaxies. They assembled along filaments of dark matter, forming the great cosmic web. Some grew into spirals, others into massive elliptical forms. The Milky Way, our home, was among them. Slowly, the structure of the universe emerged. Stars within galaxies, galaxies within clusters, clusters stretched into vast filaments surrounding immense voids. It is a pattern as beautiful as it is immense, written across billions of light years. By 1 billion years after the Big Bang, the universe was populated with stars and galaxies. Black holes formed at the heart of many galaxies, drawing in matter and powering quasars, some of the brightest objects ever seen. The great chemical cycle had begun. Stars forged elements in their cores, supernovae spread them outwards, new stars were born from that enriched gas. Each cycle created more complexity, building towards the conditions that would make planets, oceans, and eventually life itself. Today we know this story not from myth but from science. Astronomers measure the faint glow of the microwave background. Physicists replicate early conditions in particle accelerators. Telescopes peer back billions of years, watching galaxies as they were in their infancy. What we see matches the predictions of physics, a universe that began in heat and density, expanded, cooled, and grew into the cosmos we know. The Big Bang is not just a theory, it is written in the very fabric of reality. From the first second to the first billion years, the Big Bang gave us everything: the forces of physics, the elements of matter, the light of stars, and the galaxies that would cradle planets like our own. All of human history rests on this foundation. Without the Big Bang, there would be no Earth, no civilizations, no stories to tell. As we leave the cosmic dawn, we move forward in our journey to the birth of the solar system, the making of Earth, and the origins of life itself. 4.5 billion years ago, our Sun did not exist. Instead, a vast molecular cloud drifted in a quiet arm of the Milky Way. Cold and tenuous, it stretched across light years, filled with hydrogen, helium, and dust grains forged in ancient stars. Every atom carried history: the oxygen that would one day fill oceans, the calcium that would harden bones, the iron that would flow in blood, all drifted silently, waiting. This silence ended when a nearby giant star died. When the star exploded as a supernova, its shockwaves slammed into the quiet cloud. The balance broke. The gas shivered, ripping into knots. In those knots, gravity tightened its hold. Collapse began. We can still watch this today. In the Orion Nebula, stars are being born at this very moment, veiled in gas and surrounded by disks where planets are forming. Orion is a time machine, showing us the scene that once unfolded here, long before Earth existed. For tens of millions of years, the proto-sun glowed faintly, hidden by dust. Then, when its core reached 10 million degrees, hydrogen fused into helium. The star ignited. Light burst outward. The sun was born. The newborn sun was violent. Arcs of plasma erupted from its surface. Solar winds blasted outwards, stripping lighter gases from the inner solar system. This fury sculpted the planets. Mercury, Venus, Earth, and Mars became rocky. Jupiter and Saturn swelled with hydrogen and helium. The sun's tantrums decided the shape of its family. In the sun's core, hydrogen fuses into helium, releasing energy. Every second, hundreds of millions of tons of hydrogen vanish, transformed into light. That light takes thousands of years to escape, then races across space in 8 minutes to reach Earth. Fusion balances gravity. Without it, the star would collapse. With it, the star shines steadily for billions of years. Had the Sun been larger, it would have burned too fast. Smaller, and might never have ignited at all. Our Sun is extraordinary precisely because it is ordinary, stable, reliable, long-lived. The Sun carries within it the ashes of other stars. Meteorites still hold isotopes forged in supernovae, proof that a dying star seeded our solar system before it formed. In every grain of sand, every cell of life, every drop of water, those elements endure. The sun's light illuminates them, but their origin lies in older stars. We are stardust twice over. Even as the sun blazed, its disk was alive with creation. Dust grains collided and clumped, growing from grains to pebbles, pebbles to boulders. Gravity stitched them into planetesimals, worlds in miniature. Some survived, growing into planets. Others were destroyed. It was chaos. But it was also the beginning of order. Modern telescopes reveal the same process unfolding around distant stars. We see disks carved with rings where planets are forming. Each is a mirror of our own distant past. Over time, the sun's tantrums quieted. It settled into its main sequence, a stable rhythm that has lasted 4.5 billion years. Its steady light is Earth's greatest gift. A flickering or unstable star could never have cradled life, but our sun has endured, a steady flame in a turbulent universe. The Milky Way holds hundreds of billions of stars, many brighter and stranger. To the galaxy, the sun is ordinary, but for us, it is everything. 4.5 billion years ago, the sun ignited, and from its light, all life would one day come. 4.5 billion years ago, amid the relentless swirl of the solar nebula, a small region within the inner disk condensed into the third planet from the Sun. Here, silicate minerals and metallic iron accumulated into a growing protoplanet that would one day support oceans, continents, and life. But its birth was anything but tranquil. Collisions, melting, and catastrophic impacts marked its formation. The Moon itself would arise from one of these cataclysms, born of fire and debris before both worlds cooled into stability. The timeline of Earth's history comes from studying radioactive elements that decay very slowly over billions of years. By measuring uranium and lead in tiny zircon crystals, scientists find that the first solid materials in the solar system formed about 4.57 billion years ago, and Earth itself finished forming around 4.54 billion years ago. Another method, using hafnium and tungsten, shows that Earth's metal core separated from the rocky mantle within the first 30 to 100 million years after the solar system began. In short, Earth and the Moon took shape near the end of a violent period of planet building when giant collisions were still common. Within the early solar system, temperatures exceeded 1000 Kelvin. Volatile ices were absent, refractory materials dominated. The earliest solids, calcium, aluminium inclusions, and chondrules, aggregated into planetesimals thousands of kilometers across. These bodies collided, merged, and occasionally shattered, their evolution governed by gravity and chance. The growing Earth swept up smaller fragments while competing embryos, such as those that would become Venus and Mars, did the same. Computer simulations suggest that in the early solar system, between about zero point 0.5 and 1.5 times the distance from the Sun to Earth, hundreds of small worlds, each the size of the Moon or Mars, formed within a few million years. Over the next 50 to 100 million years, these bodies crashed into each other and merged, leaving behind the four rocky planets we know today: Mercury, Venus, Earth, and Mars. The way their orbits and spins balance out matches what we see today, giving scientists confidence that these models of early planetary collisions are accurate. As accretion proceeded, gravitational energy and radioactive decay heated the young planet. Iron melted and sank toward the center, forming the core, while lighter silicates rose to create the mantle. The process released latent heat, raising interior temperatures to several thousand Kelvin and keeping much of the surface molten. A global magma ocean enveloped the early Earth. When Earth's metal core formed, it released an enormous amount of energy, enough heat to keep much of the planet molten for millions of years. As the molten iron sank to form the core, it pulled down iron-loving elements such as nickel, cobalt, gold, and platinum, leaving the rocky mantle poorer in these metals. This separation also changed the mix of tungsten isotopes in the mantle. By measuring these isotopes, scientists can tell that about 90% of Earth's core formed within the first 30 million years after the solar system began. The Earth's proto-atmosphere at this stage consisted largely of hydrogen and helium captured from the nebula. Because of the Sun's strong ultraviolet radiation and planet's weak gravity, this primordial envelope was quickly lost to space, leaving behind a bare, molten world surrounded by silicate vapor. The young solar system remained chaotic. Jupiter and Saturn migrated through the disk, altering the orbits of countless planetesimals. Collisions rained debris onto the inner planets, adding mass and volatile elements. Asteroids and comets delivered water and carbon-bearing molecules to Earth's surface, though most of that surface was still molten. According to computer models like the NEAS model, after the solar system's gas and dust cleared away, about 3 to 10 million years after it formed, the pull of gravity between Jupiter and Saturn upset the balance of smaller icy and rocky bodies in the outer solar system. This caused a wave of impacts about 4.1 to 3 billion years ago, known as the Late Heavy Bombardment. Evidence from craters on the Moon shows that many impacts happened during this time. The bombardment likely melted and destroyed much of Earth's early surface, but it may also have brought in water and organic molecules from distant asteroids, setting the stage for life to begin later. The chemical makeup of Earth's water, especially the ratio of deuterium, or heavy hydrogen, to normal hydrogen, is almost the same as that found in certain carbon-rich asteroids. This means that most of Earth's water probably came from asteroids, not comets. This idea was confirmed by the Rosetta spacecraft, which measured much higher deuterium levels in the water from comet 67P, showing that comet water is quite different from Earth's. One of the last giant impacts in Earth's history was the most dramatic of all, A planet around the size of Mars called Theia crashed into the young Earth at a glancing angle and tremendous speed, around 10 kilometers per second. The collision released an enormous amount of energy, melting both worlds and throwing huge amounts of rock and vapor into space. That debris eventually came together to form the Moon. The giant impact hypothesis explains multiple lines of evidence: the Moon's large relative size, its depletion in volatile elements, and its isotopic similarity to Earth. High precision analysis shows that terrestrial and lunar rocks share nearly identical oxygen, titanium, and tungsten isotope ratios, far closer than any other solar system bodies, indicating a common origin. Computer simulations reproduce these features when the impact mixes Theia and Earth's mantles thoroughly before the debris condenses. The angular momentum of the present Earth-Moon system corresponds to a total rotational period of roughly 5 hours immediately after impact. Tidal interactions have since transferred angular momentum outwards, slowing Earth's rotation to 24 hours and pushing the Moon to its current 384,000 kilometer orbit. Ancient tidal rhythmites, sedimentary layers recording daily cycle, confirm that 2.5 billion years ago the Moon was only 60% of its current distance and days lasted 18 hours. Alternative models have been explored. Multiple smaller impacts capture scenarios of fission from a rapidly spinning Earth. None match the isotopic and dynamical data as successfully as the Theia collision. Recent refinements suggest that Theia's composition was roughly identical to Earth's, explaining the isotopic similarity, or that the impact produced a synthesis, a transient donut-shaped mass of vaporized rock from which both Earth and the Moon condensed. The Theia collision left Earth incandescent. For months or years, the surface remained an ocean of magma thousands of kilometers deep, while a dense atmosphere of silicate vapor, steam, and carbon dioxide enveloped the planet. The newly formed Moon, glowing red hot, orbited just 20,000 to 30,000 kilometers away, so close that it loomed 20 times larger in the sky than it does today. Tides between the two bodies were immense, and the Earth's rotation period may have been as short as 5 hours. Computer models suggest that after Earth's violent beginnings, the planet was covered by a global ocean of molten rock, hotter than 2,500 degrees Celsius. It cooled very slowly, taking a few million years to solidify. Early on, the atmosphere was filled with gases from vaporized rock, but as the planet cooled, these minerals condensed and fell back to the surface. This left behind lighter gases such as water vapor, carbon dioxide, sulfur dioxide, and nitrogen, which escaped from the interior through volcanic eruptions. During this time, the atmosphere may have been hundreds to thousands times thicker than it is today. When the Moon first formed, it orbited very close to Earth, only about 3 times Earth's diameter away. Its strong pull created powerful tides inside Earth's still soft mantle, which helped the planet cool faster. Over the first 100 million years, these tidal forces released almost as much energy as the Moon forming impact itself. This close relationship between Earth and the Moon also helped steady Earth's tilt, giving the planet a stable climate over long periods of time. As heat escaped into space, crystals began to form in the upper layers of the magma ocean, creating a primitive crust of anorthosite and basaltic composition. Iron and nickel continued to sink inward, completing the segregation of the metallic core and generating the magnetic dynamo that would one day shield the atmosphere from the solar wind. The remaining mantle convected vigorously, cycling material between surface and interior. Studies of earthquakes and Earth's chemistry show that the core makes up about 1/3 of the planet's mass and extends to a depth of about 7,000 kilometers. The outer core is still liquid, made mostly of iron and nickel mixed with small amounts of lighter elements like sulfur, oxygen, and silicon. Deeper down, the inner core has solidified, forming sometime between 1 and 2 billion years ago. As it froze, it released heat that keeps Earth's magnetic field running today. Evidence from tiny magnetic crystals in ancient rocks from Western Australia suggests that Earth may have had a magnetic field as early as 4.2 billion years ago. Earth's first crust was probably short-lived, constantly destroyed and remade by powerful impacts from space. But chemical clues inside ancient zircon crystals show that liquid water was already present by about 4.38 billion years ago. This means parts of Earth's surface had cooled and solidified enough to hold oceans or lakes within only 150 million years after the Moon formed. The Moon too bore the scars of its fiery origin. The debris disk that spawned it produced a body largely molten. As it cooled, lighter anorthite crystals floated to the surface, forming the bright lunar highlands, while denser materials, olivine, pyroxene, sank to create the mantle. Meteorite bombardment soon pocked its face with craters, recording the violence of the solar system's youth. Moon rocks brought back by the Apollo missions include Pharoan anorthosites, lightly coloured crustal rocks dated to about 4.36 billion years ago, showing when the Moon's global magma ocean finally solidified. Later volcanic rocks called mere basalts reveal that lunar eruptions continued on and off until about 1.2 billion years ago, long after Earth had cooled and stabilized. The chemical makeup of the Moon and Earth, including oxygen, titanium, and chromium isotopes, is nearly identical, proving that they came from the same material. Today, laser measurements show that the Moon is slowly moving away from Earth at about 3.8 centimeters per year as their gravitational tides continue to interact. With the magma ocean crystallized and impact flux declining, volatile gases began to condense. Water vapor rained out, filling the basins and lowlands to form the first oceans. Carbon dioxide and nitrogen remained in the air, creating a dense greenhouse warm atmosphere. The young sun's ultraviolet light drove photochemical reactions, producing hazes and potentially organic molecules that settled into the area. Volcanoes and heat inside the young Earth released huge amounts of water vapor and carbon dioxide, enough water to fill oceans several kilometers deep. Scientists think that most of Earth's water came from this internal source, with the rest added by impacts from water-rich asteroids. Tiny ancient crystals showed signs that liquid water existed about 4.3 billion years ago at mild temperatures around 30 to 40 degrees Celsius. This suggests that a thick atmosphere of carbon dioxide and nitrogen kept the planet warm even though the sun was dimmer than it is today. The earliest atmosphere lacked free oxygen. Instead, methane and ammonia produced a reducing environment. Lightning and ultraviolet radiation acting on these gases could synthesize amino acids and simple organics, as demonstrated in Miller-Urey type experiments. The balance of carbon between atmosphere and ocean established early chemical cycles that would later feed the emergence of life. The moon's gravitational influence quickly became a regulating force. Its tidal pull slowed Earth's rotation, lengthening the day and dampening variations in the axial tilt. Without it, Earth's obliquity might have wandered chaotically, leading to extreme climate swings. The stable tilt of 23.5 degrees, oscillating only a few degrees over tens of thousands of years, produced regular seasons that would shape future biological rhythms. Dynamical simulations comparing Earth with a hypothetical moonless planet show obliquity variations up to 60 degrees over million-year timescales. The presence of a large moon increases the planet's moment of inertia and shifts resonance frequencies away from those driven by Jupiter and Saturn. This stabilizing effect likely persisted throughout Earth's history, influencing not only climate but also tidal patterns essential to early coastal ecosystems. Meteorites preserve snapshots of the solar system's early chemistry. Astatite chondrites share isotopic affinities with Earth in oxygen, silicon, and titanium, implying they originated from the same inner solar region. Their highly reduced mineralogy supports models in which Earth accreted from material formed under low oxygen conditions inside 1 AU. Iron meteorites, remnants of differentiated planetesimals, record metal silicate separation ages consistent with Earth's core formation timeline. Collectively, these extraterrestrial samples anchor the chronology of planetary growth. No rocks older than 4 billion years still exist on Earth, but tiny zircon crystals found in Western Australia preserve chemical clues from as far back as 4.38 billion years ago. Their makeup shows they once formed in the presence of liquid water and came from recycled crustal material. These microscopic minerals prove that continental crust and stable oceans already existed very early in Earth's history, less than 200 million years after the planet was first formed. The making of Earth was a saga of accretion, collision, and transformation. Out of a disk of dust came a molten planet from a catastrophic impact, a stabilizing moon. The surface cooled, oceans formed, and the first atmosphere condensed beneath a young, brilliant sun. By 4.3 billion years ago, Earth had become a world of rock, sea, and sky, its violent infancy giving way to the long rhythms of geology and time. In the next episode, The focus will turn to Hadean Earth itself, its molten landscapes, early crust, and the gradual emergence of conditions that would one day permit life to begin. G'day everyone, I'm the Ancient Gamer, and welcome to episode 4 of the History of the World. Today we're heading back over 4 billion years to a time when Earth was a molten world of fire and chaos. We'll see how it cooled, how the first oceans formed, and how this once hellish place became ready for life. Let's dive in. I hope you enjoy the episode. The Hadean Eon, named for Hades, the underworld, spans the interval from Earth's formation about 4.56 billion years ago to the appearance of the earliest known rocks near 4 billion years ago. It was once imagined as an inferno, utterly hostile to stability. Yet modern evidence tells a subtler story, a planet alternately molten and solid, bombarded yet persistent, already forming crusts, oceans, and perhaps transient niches of hospitality. The Hadean Eon was Earth's apprenticeship, its transition from cosmic debris to enduring world. The term Hadean entered geology in 1872, coined by geologist Preston Cloud, but the concept of an earliest rock-free interval gained scientific traction only with isotopic dating of zircon grains in the 1990s. These zircons, up to 4.38 billion years old, showed that stable crust and liquid water existed within 150 million years of formation, overturning the older vision of a perpetually molten Earth. After the Theia impact, Earth glowed like a miniature star. Surface temperatures exceeded 2500 Kelvin. Magma convected from core to the surface. Immense heat flux kept the atmosphere filled with silicate vapor. Yet beneath the chaos, processes of separation and order were underway. Iron and nickel sank towards the center, while lighter silicates crystallized upward, initiating the planet's layered structure. After the giant impact, Earth was covered by a deep ocean of molten rock, at least 1,000 kilometers thick and perhaps reaching all the way down to the core. At first, the planet lost heat by glowing it away into space. Later, as a crust began to form, cooling slowed. On average, the temperature dropped by only about 1 degree every 100 years, meaning it took several billion years for the surface to harden. During this time, heat surged upward through powerful currents, churning the molten layers into a vast, fiery sea. As the molten surface of the young Earth began to cool and solidify, gases trapped inside the liquid rock, like water vapor, carbon dioxide, sulfur dioxide, and nitrogen, started to escape into the air. Even a tiny amount of water released this way would have been enough to fill today's oceans. This means much of Earth's water likely came from deep within the planet itself, not just from icy comets striking from space. As metallic iron segregated into droplets and diapeds, it descended through molten silicate, releasing gravitational energy and forming the dense core. Lighter materials enriched the mantle in oxygen, silicon, and magnesium. The segregation also trapped heat-producing elements, uranium, thorium, and potassium, preferentially in the mantle, establishing the long-term engine of plate tectonics. Studies of earthquake waves reveal that Earth's core is about 3,480 kilometers in radius and makes up roughly one-third of the planet's total mass. The outer part of the core is still molten, kept hot by leftover heat from Earth's formation and by the slow decay of radioactive elements. Scientists date when the core formed by studying tiny differences in certain elements, hafnium and tungsten, because hafnium stays in rocky material while tungsten moves into metal. The point when these two become separated marks the birth of the core. Measurements show that this happened very early, within 30 million years after the solar system began. The onset of the geodynamo may have occurred as early as 4.2 billion years ago, according to paleomagnetic signals preserved in Jack Hill's zircons. If correct, Earth possessed a protective magnetic field long before its surface stabilized, shielding nascent atmospheres from solar wind erosion. As the magma ocean cooled, buoyant plagioclase and pyroxene crystals accumulated near the surface, thickening into a primitive basaltic crust. Convection beneath continually recycled this crust, but portions survived long enough to interact with water and generate the earliest sediments. Scientists study ancient mineral grains called zircons, tiny crystals that have survived since the Hadean eon, to learn what Earth's first crust was like. The chemical fingerprints inside these zircons shows that the rocks they came from had once interacted with liquid water, meaning parts of the surface were already cool and stable. Other clues suggest that this early crust wasn't just raw volcanic rock from the mantle, but had been melted and reformed, producing a lighter, more continental type material. In short, Earth may have had its first small continents as early as 4.3 billion years ago, hundreds of million years earlier than scientists once thought. The survival of such crusts may reflect a stagnant lid regime rather than modern plate tectonics. Heat flow, 3 times present levels, would have driven rapid magmatism but not necessarily subduction. Islands of felsic rock could have formed through partial melting of hydrated basalts in impacted basins, rising as lighter, silicate-rich domes, precursors to continents. Above the molten surface hung a dense atmosphere, first of silica vapor, then of steam, carbon dioxide, and nitrogen. As cooling continued, the silica components condensed and rained out. Water vapor dominated, forming a global greenhouse that prevented rapid freezing even under the faint young sun. As Earth's surface began to cool below 2000 degrees Celsius, many of the heavier gases, those containing magnesium, silicon, and iron, condensed and fell back to the surface. What remained was an atmosphere made mostly of water vapor, about 90%, with smaller amounts of carbon dioxide, nitrogen, and traces of sulfur dioxide. The air pressure was enormous, hundreds of times greater than today's. Because the young sun was much dimmer, this thick, carbon dioxide rich atmosphere acted like a powerful greenhouse, trapping heat and keeping the planet warm enough for liquid oceans to exist. Hydrogen, the lightest component, escaped rapidly to space, fractionating isotopes and leaving a heavier DH ratio, now reflected in Earth's oceans. The early loss of hydrogen also rendered the atmosphere progressively more oxidized, setting redox conditions that would later govern prebiotic chemistry. Even as the crust solidified and oceans began to gather, the young Earth remained under constant siege. The solar system was still clearing itself of leftover debris. Asteroids, comets, and planetesimals swept across interplanetary space, drawn into collision courses by gravitational perturbations from the giant planets. Each impact released more energy than all modern volcanoes combined, reshaping the surface and periodically vaporizing parts of the new crust. Crater statistics from the Moon, whose ancient surface preserves what Earth's active geology has erased, shows that bombardment rates declined steeply after 4.4 billion years ago but remained high for several hundred million years. A possible surge between 4.1 and 3.8 billion years, the late heavy bombardment, is recorded in lunar basins such as Imbrium and Orientale. On Earth, such events would have generated transient seas of magma hundreds of kilometers wide and thick atmospheres of rock vapor. Impact modeling indicates that the largest projectiles, 100 to 300 kilometers across, could have globally melted the upper mantle, while smaller but more frequent impacts excavated vast basins that filled with meltwater soon after cooling. Hydrothermal systems around these craters may have been transient refuges for emerging chemical complexity, periodically destroyed and renewed by the next wave of impacts. As bombardment waned and atmospheric temperatures dropped below the critical point of water, 647 Kelvin, condensation began in earnest. Steam thickened into rain, and for the first time, water pooled on the surface. The first oceans were likely hot, mineral rich, and acidic from dissolved CO2, but they represented a permanent change. Earth had become a water world. Scientists estimate that Earth's first oceans may have held a little more water than today, perhaps about 10 to 30% more, released from deep inside the planet as it cooled. Tiny crystals called Hadean zircons show chemical signs that liquid water already existed on the surface, at mild temperatures around 30 to 40 degrees Celsius. To keep the planet warm under a dim young sun, the atmosphere was likely packed with carbon dioxide, creating a powerful greenhouse effect. Even in the presence of high impact flux, water would have quickly recondensed. Numerical simulations show that a full vaporization of the oceans by a Chicxulub scale impact, a 10-kilometer body, would last less than 10,000 years before condensation resumed. Thus, despite intermittent cataclysm, surface water was a permanent feature by 4.3 billion years ago. The oldest known minerals on Earth, tiny zircon crystals found in the Jack Hills of Western Australia, are over 4.3 billion years old. Their chemistry shows that they formed in molten rock that had come into contact with liquid water, meaning oceans already existed at this time. Though each crystal is smaller than a grain of sand, they survived countless cycles of erosion and burial before settling into younger rocks. These zircons are our best proof that both oceans and pieces of early continental crust appeared very soon, within about 150 million years after Earth first formed. The early atmosphere changed quickly. Massive volcanic eruptions kept releasing gases from deep within the Earth, replacing the carbon dioxide, water vapor, and sulfur gases that had been stripped away by impacts and weathering. Light hydrogen drifted off into space, leaving the planet's surface gradually more oxidized. With no life yet to produce oxygen, methane and ammonia filled the air instead, creating a thick orange haze under the sun's ultraviolet light and trapping heat to keep the young planet warm. Computer models suggest that when early Earth's atmosphere contained enough methane, it could have developed a thick orange haze like the one seen on Saturn's moon Titan. This haze would have blocked out harmful ultraviolet light from the sun and helped keep the planet's surface warm, around 17 degrees Celsius. Energy from lightning, volcanoes, and sunlight breaking apart methane and ammonia could then create simple organic molecules such as hydrogen cyanide and formaldehyde, the basic ingredients needed for the first steps towards life. Chemical traces in ancient sulfur found in very old rocks show that before about 2.4 billion years ago, Earth had no protective ozone layer. Sunlight could directly break apart sulfur gases in the atmosphere, a process only possible when there was little or no oxygen. This evidence supports the idea that early Earth's air was very different from today's, made up of gases that created a much more chemically reducing environment. By 4.2 billion years, the planet's surface had diversified. Regions of felsic crust, enriched in silica and aluminium, floated atop denser basaltic plates. In low-lying areas, oceans collected and began cycles of sedimentation and weathering. Carbon dioxide dissolved in seawater, forming carbonate minerals that sequestered carbon and moderated climate. The crust thickened, mantle convection slowed, and the planet approached a dynamic equilibrium that would persist for eons. Computer models suggest that around 4 billion years ago, Earth's interior was much hotter than it is today, about 250 to 350 degrees hotter. This intense heat drove widespread volcanic activity, but also meant the planet was cooling quickly. When water-rich volcanic rocks deep in the crust partially melted, they produced light-colored granitic rocks known as TTGs. These ancient rocks became the foundations of Earth's first continental cores, parts of which still survive today in regions like Canada, Greenland, and Western Australia. Numerical convection studies show that even without full plate tectonics, delamination of dense lower crust could recycle material into the mantle, producing isotopic signatures later inherited by Archean rocks. Thus, protoplate behavior may have begun as early as 4.2 billion years ago, bridging the gap between a stagnant lid Hadean and the mobile plates of later eras. The newly formed Moon continued to orbit close enough to raise tides hundreds of meters high in the first oceans. These tides stirred coastal zones, mixed nutrients, and may have influenced the chemical gradients that later favored life. Tidal friction gradually lengthened Earth's day from perhaps 5 hours to 10 by 4 billion years ago and steadily moved the Moon outward to about 200,000 kilometers. The regular rhythm of tides imposed a daily cycle that would become a fundamental environmental constant. Libration models show that within 100 million years of formation, tidal dissipation in Earth's molten mantle reduced its rotation rate by half. The tidal torque also stabilized the axial tilt, limiting obliquity variations to less than 5 degrees, ensuring climatic predictability over geological timescales. These seemingly mechanical adjustments provided a foundation for later biological stability. By the close of the Hadean, around 400 billion years ago, Earth had cooled enough for solid crust, liquid oceans, and an active hydrologic cycle to persist. Volcanic islands dotted the seas, hydrothermal systems pulsed along rifts and impact basins, and a thick, chemically rich atmosphere wrapped the planet. The basic ingredients for life, liquid water, carbon compounds, energy gradients, and mineral surfaces, were present. The planet was no longer a cosmic furnace, but a dynamic laboratory. The earliest possible signs of life appear in rocks from Greenland that are about 3.83 billion years old. These rocks contain a special carbon pattern that looks like it was shaped by living organisms. Scientists still don't know if life had already begun before this time and managed to survive heavy asteroid impacts, or if it started afterwards. In laboratory experiments, researchers have shown that under conditions similar to early Earth, simple gases can react to form the building blocks of life, like amino acids and the bases found in DNA, showing that life could have begun naturally, even if we don't yet have direct proof. Hydrothermal vents, especially alkaline types rich in serpentinized ultramafic rocks, produce proton and redox gradients capable of driving prebiotic reactions. These environments existed as soon as ocean crust interaction began, perhaps by 4.3 billion years, offering continuous energy sources shielded from surface impacts. The Hadean Earth began in cosmic violence and ended in comparative calm. Out of molten chaos came oceans, from constant bombardment a stable crust, from toxic gases an atmosphere that would one day nurture life. In scarcely half a billion years, the planet transformed from a glowing sphere of magma to a world of seas, continents, and cycles of wind and rain. When the curtains of fire lifted, the stage was ready for the next act in planetary history, the appearance of the first sparks of life. And that's how our planet turned from a world of molten rock into one filled with oceans, clouds, and the chemistry of life. The stage was set, the chaos had ended, and the first whispers of biology were about to begin. If you enjoyed this journey into Earth's fiery beginnings, make sure to like, subscribe, and stay tuned for episode 5, where we'll explore the first sparks of life in the ancient oceans. Thanks for watching. I'm the Ancient Gamer, and I'll see you in the next episode.